Sometimes our higher order differential equations aren't homogeneous, so they actually equal some function of x. And today, what we're going to do is we're going to look at a method called the method of undetermined coefficients. Specifically, we're going to look at the Annihilator approach to that method as a method for solving these non-homogeneous differential equations with constant coefficients still. Earlier in this block of material, we talked about a thing called a differential operator. And what this was it was some function that basically was telling us to take derivatives. So whenever I saw d to the kth power times y, what that was doing was telling me to take the kth derivative of y with respect to x. And we were able to make linear combinations of these. We could take a sub n times d to the n times y, plus keep on going down in power to a sub 1 d to the first power times y, plus a sub 0 times y equals g of x. And that was called a linear operator. Today we're going to be considering the linear operator L of y equals g of x, where L is going to be the operator a sub n d to the n plus, all the way down to a sub 1 times d plus a sub 0. Notice that this looks like a polynomial where d is my variable. So I can factor these. So say I have the equation y double prime plus 5y prime plus 6 equals 0. Writing that with differential operators as a linear operator is going to be d squared plus 5d plus 6 equals 0. Now I notice I can factor this as d plus 3 times d plus 2 equals 0. Or I could write it as d plus 2 times d plus 3 equals 0. So these factors that involve differential operators are commutative, just like they would be if it was any other variable. In order to talk about our annihilator approach to the method of undetermined coefficients, we need to know what an annihilator is. An annihilator is a specific type of differential operator. So if L is a linear differential operator with constant coefficients, and f is a sufficiently differentiable function such that L of f of x equals 0, then L is said to be an annihilator of the function. So L basically destroys the function. It takes the derivative so many times that it destroys the function. So there are some common annihilators that we can talk about. Namely, d to the n is going to annihilate anything that looks like 1, x, x squared, x cubed, all the way up to x to the n minus 1. As long as the exponent on our variable x is smaller than the exponent on our annihilator d, then it's going to annihilate. Another common one is d minus alpha, that quantity, raised to the nth power. This is going to annihilate functions that look like e to the alpha x, or x times e to the alpha x, or x squared times e to the alpha x, and so on, as long as the x out in front of the e to the alpha x has a power, again, that's smaller than n if our annihilator is raised to the nth power. And a final common annihilator is one that annihilates trig functions for us. So the quantity d squared minus 2 alpha d plus the quantity alpha squared plus beta squared raised to the nth power is going to annihilate e to the alpha x cosine of beta x, x e to the alpha x cosine of beta x, all the way up to x to the n minus 1 e to the alpha x cosine of beta x. I can replace the cosines with sines. They're interchangeable there for it being able to annihilate. And again, as long as the exponent on x is smaller than the exponent on the annihilator, this will work. So we have those three common annihilators that we can use as we talk about the method of undetermined coefficients. Now, hopefully in talking about those common annihilators, you've come to the conclusion that there are in fact many annihilators for any one function. Say my function is simply x. Well, things that are going to annihilate x could be d squared, d cubed, d to the fourth, d to the fifth, and I could keep on going. So annihilators, they're not unique. We have multiple annihilators for any given function. So our common practice is to use the one with the lowest possible order in order to make our lives just as simple as they can be. So now with all of that in our pocket, we're ready to talk about the method of undetermined coefficients with our annihilator approach. So if we have the differential equation L of y equals g of x, and it has constant coefficients, and the function g of x consists of a finite sums and products of constants, polynomials, exponential functions, sines, and cosines, then we can use this approach. So once we've determined that we can use this approach, then we're going to go through a series of 6 steps. The first one is to find the complementary solution, y sub c, for the homogeneous equation L of y equals 0. So replace g of x with 0, find the solutions to that differential equation. There will be one solution, we'll name it y of c, and we'll be coming back and using it in a little bit. Set that aside, and then what we're going to do is we're going to determine an annihilator for the function g of x. So again, smallest order, meaning smallest exponent, that n value needs to be as small as possible for a differential operator that's going to annihilate g of x. Once you've determined that, we're going to name it L1. We're going to operate on both sides of our non-homogeneous equation. So that'll give us L1 of L of y equals L1 of g of x. L1 of g of x is going to give us 0 since L1 is an annihilator of g of x. So that's going to leave us with the function, the equation, L sub 1 times L of y equals 0. So now I have a higher order homogeneous differential equation in L sub 1 L of y, and I can find a general solution to that higher order homogeneous differential equation. So now, after I've solved that and I've found the general solution for my higher order homogeneous differential equation, there's a chance that there's going to be terms in that general solution that I found that are also in y sub c that I found back in my first step and set aside. I don't want 2 copies of each of those terms. I only want a single copy of them. So from my general solution of the higher order homogeneous differential equation L sub 1 times L of y equals 0, I'm going to delete all of the terms that are duplicated in that complementary solution that I found in my first step. Then I'm going to form a linear combination of the terms that remain. This is going to be the form of a particular solution of L of y equals g of x. So this is going to be the solution that we're going to call y sub p. So that y sub p that we found in that step 4, we're going to substitute it into L of y equals g of x. And we're going to match coefficients of our various functions on each side of the equality and solve the resulting system of equations for the unknown coefficients in our particular solution, y sub p. In solving for those unknown coefficients, what we're going to do is we'll have a particular solution with those coefficients plugged in that we can use to form the general solution y equals y sub c plus y sub p of our given differential equation. And at this point, we will have determined the solution to the original non-homogeneous differential equation that we set out to solve using this method of undetermined coefficients. This may seem like a lot, and it kind of is. So let's take a look at an example of how this works so that hopefully it seems a little bit more approachable. So here I have a non-homogeneous second-order differential equation with constant coefficients. So I can use the method of undetermined coefficients. So my equation is y double prime plus 3y prime plus 2y equals 4x. So my first step to all of this is to find the complementary solution for the homogeneous equation that I get when I set L of y equal to 0. So rewriting this with differential operators, then I have d squared plus 3d plus 2 equals 0. And that's the one that I'm trying to find solutions to. So I can do this by using my auxiliary equation, which is m squared plus 3m plus 2 equals 0. So I can factor this to m plus 2 times m plus 1 equals 0. And I can solve this to find m equals negative 2 and m equals negative 1. So I have two distinct real roots. Consequently, my complementary solution, y sub c, is going to equal c1 e to the negative 1 times x plus c2 e to the negative 2 times x. So that completes step 1. Step 2 says operate on both sides of the non-homogeneous equation L of y equals g of x with a differential operator that annihilates the function g of x. My function g of x is 4 times x squared. To annihilate x squared, I need to take the third derivative, so I need to use a differential operator of d cubed. So for step 2, I'm going to be multiplying both sides of my differential operator form of my differential equation by d cubed. So when I do that, I'm going to end up with d cubed times the quantity d squared plus 3d plus 2 times y equals 0, since d cubed annihilates x squared. And that's the end of my second step. My third step says find the general solution of the higher order homogeneous differential equation L sub 1 times L of y equals 0. So I need to find the general solution of my higher order homogeneous differential equation d cubed times the quantity d squared plus 3d plus 2 times y equals 0. So I'll use an auxiliary equation here. My auxiliary equation will be m cubed times the quantity m squared plus 3m plus 2 equals 0. And we've already factored that second part, so I could instead write it as m cubed times m plus 2 times m plus 1 equals 0. Now, looking at the roots of this, m cubed equals 0 is going to give me 3 roots that are all 0. So I'll have m sub 1 equals m sub 2 equals m sub 3 equals 0. So I have that repeated root. And then I still have my roots of m sub 4 equals negative 2, m sub 5 equals negative 1. So with my repeated roots and my two other roots, I'm going to end up with a solution that looks like y equals c1 e to the 0 plus c2x e to the 0 plus c3 x squared e to the 0. That deals with my repeated roots. And then I'll also have these two other roots, so I'll also be adding in some other constant, c4 e to the negative 2 x plus c5 e to the negative x. And at this point, we've completed step 3. And we're ready to complete step 4. So let's take a look at step 4. It says delete from the solution in step 3 all those terms that are duplicated in the complementary solution y of c found in step 1. Form a linear combination of the terms that remain. This is the form of a particular solution. All right. So I'm going to take my solution that I had in 3 and I'm going to turn it into my particular solution by writing all of the terms that are in this solution that I got in 3 that are not in y sub c from step 1. So y sub c from step 1 does not have a c1 e to the 0. It does not have a c2x e to the 0. It does not have a c3 x squared e to the 0. It does have a constant times e to the negative 2x, and it does have a constant times e to the negative x, so I'll leave those two terms out. So I'm going to write this, and I'll end up with c1 e to the 0 is just 1, so I don't need to write it, plus c2 times x, again e to the 0 is 1, and plus c3 x squared, again e to the 0 is 1. So this gives me my particular solution. And that completes step 4. So now step 5 says it wants me to substitute my particular solution that I had just arrived at into L of y equals g of x. I'm going to match coefficients of the various functions on each side of the equality and solve the resulting system of equations for the unknown coefficients in y sub p. This is the step that seems the strangest, I think. So in order to do the substitution, I need both first and second derivatives of my particular solution here. So I'm going to solve for those first. So the first derivative of y sub p is going to be c sub 2 plus c sub 3 times 2x. And my second derivative of p is going to be c sub 3 times 2. So then I'm going to take all of these parts and I'm going to substitute them into my original equation. So the second derivative, or 2c sub 3, plus 3 times the first derivative, so 3 times c2, plus 3 times 2, or 6 times c3 times x, plus 2 times y, so 2 times c1, plus 2 times c2 times x, plus 2 times c3 times x squared is going to equal 4x squared. So I've done the part where it says to substitute this in. Now it tells me to match coefficients of the various functions on each side of the equality and solve the resulting system of equations. When it tells me to do that, what it's telling me to do is to say, what are the powers of x here? So I have 4x squared, and I have 2c3x squared, and no other x squared terms. I have 2c3 as a constant, 3c2 as a constant, 2c1 as a constant, And that's all the constants. So I've accounted for them. And then finally, I have 6c3x and 2c2x, and those are all of the x terms. So if I match these up, what I get from my constants is that 2c3 plus 3c2 plus 2c1 must equal 0 because there are no constants on the other side of the equal sign. With my x terms, I find that 6c3 plus 2c2 must equal 0 because there's no x term on the other side of the equal sign. And finally, I know that 2c3 must equal 4, since 4 is the coefficient on the x squared term on the other side of the equal sign. So now I have a system of equations that I can solve. So if I do that, 2c3 equals 4 tells me that c3 must equal 2. Plugging that in, then I know that 6 times 2 plus 2c2 equals 0, which tells me that c2 must equal -6. And then plugging in both of those, I have that 2 times 2 plus 3 times -6 plus 2c1 equals 0. And solving that for c1, I have that c1 must equal 7. So step 5 had told me that I needed to match coefficients of the various functions on each side, solve the resulting system of equations for the unknown coefficients in y sub p. So I've solved for all of my coefficients, so the only thing that's left to do is substitute them back in. So y sub p is going to equal c1, which we now know is 7, plus c2, which we now know is -6 times x, plus c3, which we now know is 2 times x squared. And that completes step 5. And finally, we have step 6. So with our particular solution that we just found, and our general solution form that we know, that's y sub c plus y sub p, and we already know what y sub c is also, then we have our general solution of our differential equation. So to finish this off, all we have to do is take our y sub c and add it to our y sub p. So y equals y sub c plus y sub p. Y sub c was c1 e to the -x plus c2 e to the -2x, and y sub p is plus 7 minus 6x plus 2x squared. And that is our general solution and the end of step 6. So now we have a solution to our differential equation using the method of undetermined coefficients.